Fun. So we were covering dynamic programming in Golang, and in this video we will be covering another exciting problem in dynamic programming. It is called longest common subsequence. So consider we have been given two strings. First one is this one and second one is this one, and in this problem we are supposed to answer that what will be the common subsequence that will be having a larger length. So for instance, in this particular string, if we take A, D and H, similarly in second string, if we take A, D and H, then its length is the ADH is a subsequence and its length is 3, and in these two strings this is the common subsequence that is of length 3 and which is the largest, right? So let's see how to solve this problem. So if you remember our knapsack program, there in each and every cell or element we had the choice. So similar to that, we have a choice whether, so for instance, if we are on this particular index of this string, so we have a choice, for instance this particular index matches another index, so in that case we have found one match. Else what we are going to do, if we do not have a match, say H and R are different, so we can either include this particular string, and in that case I'll be not including that particular substring, or if I include this one, I do not include this particular substring. So in that case we have the choices, and when we have a choice we can build a solution similar to what we did with knapsack. So let's first try its recursive solution, and then after that we will be trying to convert that recursive program into DP using a matrix where we are going to store subproblems into the cells and building onto the final solution based on the subproblem that we have solved. So let's take a function subsequence. It will be having string A comma string B, and it will also be having an index at that point of time. So if I and j, those will be the indices for corresponding string A and another string B. So going forward, what you do? So the problem, first thing is to check for the base case. The base case is if we have I equals to 0, j equals to 0, then we just return 0. So if both of the string have a length 0 or another length, if either of the string have length 0, then our solution is 0. Answer is 0. Next one, okay, it will be R. So first case will be if we find a match. In that case, A dot, so A of I equals to A of j. In that case we return, now our length is 1 because that is match, and then we solve for the sub problems. So A comma B comma I minus 1 comma j minus 1. Yeah, next is we do not have a match. In that case we will be doing a max. That's because we have to maximize or find the subsequence with the maximum length. So I'll quickly again write a max, or I already have a max function, right? in our previous solution. So that will be max of a comma b. And when I take the element max of subsequence, comma subsequence a comma b. This time I ignore j and solve it for. Right, so this is our recursive solution likely. Now it's also important to kind of cache few solutions. For instance, in this particular subsequence, I and j are variable, so we can cache the solution, cache the return of this subsequence, because we also have repeated subproblems that we might solve in these function calls. So to avoid to solve those subproblem multiple times, we can just cache it. I guess I already have a cache. So fmt printf %s %d dot %d. It will be I comma j. Yeah, if I've already solved it for I comma j, cache of if it's value comma okay. I just return v as I solve it here. Similar to this one, I do it here. And then it is calculated. So this is also this solution is also called memoization. In this one, instead of solving the subproblem multiple times, we are just caching and storing the result in the cache that we have already defined. So if you are wondering what this cache is, it's nothing but a map that we already used in our knapsack solution. If you haven't watched the snapsack solution, just go back to video 001 and you will be able to see how we are using caching in knapsack. So same cache we use to cache the results of this LCS. Right, so next just call this func lis. So I'll create first string, second string, the problem. There is subsequence a comma b comma I. So if you go to this knapsack solution first here, right, so here I'll go less than 0 because that's what our termination is, because a of 0 or b of 0 is still a subsequence or a character, or in Golang it's a un at index 0. So our recursion will terminate when anytime we are going less than 0. Not sure what's the problem here. Oh, I guess I used incorrect commas. No, this will be len of a minus 1, len of b -1, and I'm going to just print this. This should print 3 as our solution. So let's see. I'll comment out this. Sol lis LCS common subsequence lis we haven't touched upon yet, so let's see. Oh, strange, it printed 6. Let's see what's the problem. So we started A, started B, len of A, len of B. Anytime it goes -1, we return 0. We also see the cache. Yeah, if we already have an element in the cache, we just return that. I and J. So we return the value. If A of I, P of J, that is the problem. Now let's again try to run this, and we got the expected answer. Yeah, so guys, I hope this longest common subsequence made sense. It's similar to knapsack, and then in our next video we will be converting this recursive solution to DP solution, and it will be very straightforward as we did in knapsack. It was just converting these particular calls to a matrix and solving subproblem as the cell of that particular matrix, and in our final cell we will be having the answer to this subsequence problem. Alright guys, so thank you for watching this video, and next video will be just converting this longest common subsequence to a DP program. Alright, thank you, bye.